Good morning, students. Today we will go through what is a Wien bridge oscillator. So this is the circuit diagram of the Wien bridge oscillator. We know that oscillator is a circuit which generates oscillations without any input signal. And there are two stages in the oscillator. One is the amplifier stage, right, and another one is the feedback stage, right. The amplifier stage, this we saw in the last class when we discussed about the RC phase shift oscillator. The output of the amplifier stage is applied as input to the feedback stage. So this is amplifier stage, its output is applied to the terminals 1 and input V into feedback network is between 1 and 3. So here we are applying the input to the feedback network. From the amplifier stage we are applying input to the feedback network to the pin terminals 1 and 3, and output of the feedback network, output VF of the feedback network is between 2 and 4. So between 2 and 4 terminals, here the output of this feedback network is applied as input to the amplifier stage. Okay, so here there is a combination of R1 C1, R3 R2 C2 in parallel, and we have a R4 resistor. So this is the Wien bridge oscillator redrawn here. So here R1 C1, it is in between terminals 1 and 4, R1 C1 in series. So here it is shown R1 C1 in between terminals 1 and 4 in series. Then between 4 and 3, so this here comes the ground terminal, it is 3 terminal 3. Between 4 and 3 we have R2 and C2 in parallel. Between 4 and 3 we have R2 and C2 in parallel. So that comes here R2 and C2 in parallel between 4 and this is terminal 3, which is grounded here, right. And this resistance and R3 and R4 has their very small values of resistance, so it is considered as a short here. So as it is a short, it is connected to ground. So here it comes the terminal number 2 also. So wherever there is terminal 3, so in between 4 and 3 we have parallel combination of R2 C2, and also terminal 2 comes at the same node as that of terminal 3, because the resistances R3 and R4 are considered as short because they are of smaller values of resistance. This R1 C1 is considered as impedance Z1, and parallel combination of R2 C2 is considered as impedance Z2. This is the input voltage that is applied as input to the feedback network, that is V in between terminals 1 and 3. In between terminals 1 and 3, here we can see in between terminals 1 and 3 the input to the feedback network is applied, and the output of the feedback network is between terminals 2 and 4. Output of the feedback network is from terminals 2 and 4, that is applied as input to the amplifier stage. Okay, so in between terminals 2, this is terminal 2 which is grounded. In between terminal 2 and 4 we have the feedback voltage which is applied as input to the amplifier stage. So let us derive the frequency of oscillation equation for the Wien bridge oscillator. In the last class we derived the frequency of oscillation equation for the RC phase shift oscillator. Now we will be deriving the frequency of oscillation equation for the Wien bridge oscillator. Here Z1 is equal to, Z1 is given by R1 plus 1 upon j omega C1. It is a series combination of R1 and C1. So Z1 will be R1 plus 1 upon j omega C1. So if we simplify this, we'll get j omega C1 is the LCM. So it will be R1 plus j omega C1 R1 divided by j omega C1. 1 plus j omega R1 C1 divided by j omega C1. Then Z2 is equal to R2 parallel C2 here. So that we will be writing it as Z2 is R2 parallel 1 upon j omega C2, because it's a capacitance which is there. So it will be 1 upon j omega C2. R2 parallel 1 upon j omega C2. And if we take the parallel of these two, we'll get R2 into 1 upon j omega C2 divided by R2 plus 1 upon j omega C2. That is R2 divided by j omega C2 divided by R2 plus 1 omega j omega R2 plus 1 upon j omega C2. That comes out to R2 divided by j omega C2. J omega C2 is LCM here, so it is R2 into j omega C2 plus 1 divided by j omega C2. J omega C2 cancels, so we get Z2 is equal to R2 divided by 1 upon R2 divided by 1 plus j omega R2 C2. Take it as equation 1. Now wherever there is j omega, replace it by s. S is equal to j omega. We know that j omega is equal to s. So wherever there is j omega, replace it by s. So z1 will be equal to 1 plus s. Instead of j omega, we are substituting as s. So 1 plus s r1 c1 divided by s c1, and z2 will be equal to r2 divided by 1 plus s r2 c2. Here I is equal to, what is current I? Current I that is flowing into this path from 1 to terminal 3, or from terminal 1 to terminal 2, is the total voltage divided by total impedance, right? That the current that is flowing in this combination, it is through R1 C1 and through the parallel combination of R2 C2. The current that is flowing, it is given by the total voltage V in divided by the total resistance Z1 plus Z2. So here we are having I is equal to V in divided by Z1 plus Z2. Now what is feedback voltage? Feedback voltage is here across terminals 4 and terminals 3 or terminal 2, that is nothing but the impedance Z2. That is the across the voltage across impedance Z2, that is nothing but the feedback voltage. So it is the current I multiplied by the impedance Z2. Total current I multiplied by impedance Z2, that gives the feedback voltage Vf. Vf is equal to I into Z2. This can also be written as the voltage across impedance Z2. It is the main voltage V in into resistance of the same branch, that is Z2, divided by sum of the resistances Z1 plus Z2. This is according to the voltage divider rule. That is here the voltage V, that is voltage Vf is equal to V in into Z2 divided by Z1 plus Z2. It is the total voltage V in into impedance of the same branch, that is Z2, by sum of the resistances Z1 plus Z2. Okay. Then here we are taking that Vf divided by Vf divided by Vin as beta. So Vf divided by Vin is taken as beta here. Beta is equal to Vf by Vin. So rearrange the terms here. Vf divided by Vin, that gives the beta. Gives the beta. That is Z2 divided by Z1 plus Z2. Okay. That is Z2 divided by Z1 plus Z2. Substitute the values of Z1 and Z2. So beta will be equal to, what is Z2? Z2 is R2 divided by 1 plus S R2 C2, and Z1 is 1 plus S R1 C1 divided by S C1. Fine students, substitute that. Beta is equal to R2 divided by 1 plus S R2 C2 divided by Z1 is 1 plus S R1 C1 by S C1, plus Z2 is R2 divided by 1 plus S R2 C2. That is R2 divided by 1 plus S R2 C2, that divided by 1 plus SR1 C1, LCM will be SC1 into 1 plus SR2 C2. So here it is, this will be multiplied by this term, that is 1 plus SR2 C2, plus R2 will be multiplied by this term, it is SC1, that divided by the LCM is SC1 into 1 plus SR2 C2. So next, to simplify this further, R2 divided by 1 plus SR2 C2, that divided by means it will be cross multiplied with SC1 divided by, that is SC1 into 1 plus SR2 C2, SC1 into 1 plus SR2 C2 divided by this term, that is 1 plus SR1 C1 into 1 plus SR2 C2 plus SC1 R2. So what cancels here, students? 1 plus SR2 C2, 1 plus SR2 C2 cancels here. Therefore, beta will be equal to R2 SC1, that divided by 1 plus SR1 C1 into 1 plus SR2 C2 plus SC1 R2. Or beta is equal to R2 SC1 divided by 1 plus, multiply here, multiply 1 into 1 is 1 plus SR2 C2 plus SR1 C1 plus this into this is SR1 C1, and this into this term SR1 C1 into SR2 C2 will be S square R1 R2, right, C1 C2, then plus SC1 R2. That comes out to, students, beta is equal to S C1 R2 divided by, take 1 plus S common, so it will be R1 C1 plus R2 C2 plus this one, that is C1 R2 plus S square into R1 R2 C1 C2. Okay. Okay, everybody are following here, students? Yes. Next, replace S by J omega. We know that S is J omega, so replace S by J omega, right? So S square will be equal to, if you take the square of this, it will be J square omega square. J square is minus 1, so it will be minus omega square. S square will be minus omega square. That is beta is equal to J omega. Beta is equal to, S is J omega C1 R2, J omega C1 R2, that divided by 1 minus here s square is minus omega square. So it is 1 minus omega square r1 r2 c1 c2. It is 1 minus omega square r1 r2 c1 c2 plus remaining term. The s is j omega into r1 c1 plus r2 c2 plus r2 c1. So j omega into r1 c1 plus r2 c2 plus r2 c1. Number this as equation 3. Let us rationalize the denominator here. So if you rationalize the denominator, then denominator is of the form a plus b. So it will be a minus b multiplied by numerator multiplied by a minus b, and denominator also multiplied by a minus b. Okay, we are rationalizing the denominator. That is beta is equal to j omega c1 r2. This multiplied by, this is 1 minus omega square r1 r2 c1 c2. This will be minus, we are rationalizing, minus j omega into r1 c1 plus r2 c2 plus r2 c1, that divided by 1 minus omega square r1 r2 c1 c2 the whole square. So in the denominator it will be a plus b into a minus b. It is a square minus b square. Fine. That is 1 minus omega square r1 r2 c1 c2 square minus j omega minus j square omega square minus j square omega square. That is j square is minus 1. So minus 1 into minus 1 is plus. Yes. So plus omega square into r1 c1 plus r2 c2 plus c1 r2 or r2 c1 square. That is beta is equal to j omega c1 r2. Here we are multiplying, right? So it is minus j omega cube minus, so j omega c1 r2, this we are multiplying inside, minus this will be j omega into omega square j omega cube c1 square, okay, r2 square, then r1 c2 r1 c2, then multiply here also. So j omega c1 r2 in minus j omega r1 c1. So it will be minus in j into j minus j square omega into omega omega square, then c1 r2, c1 into c1 is c1 square, right? Then r1 r2 r1 r2. Similarly multiply j omega c1 r2 with minus j omega r2 c2 minus j omega r2 c2. It comes out to minus j omega into minus j omega is minus j omega j square omega square, then c1 r2 into r2 c2. So it is c1 r2 square c2 c1 r2 square c2, right? And last term j omega c1 r2 into minus j omega r2 c1. So it is this will be j omega into j omega is j square omega square j square omega square, right? c1 r2 into r2 c1, that will be c square c1 square r2 square, that divided by 1 minus omega square r1 r2 c1 c2 the whole square plus omega square into r1 c1 plus r2 c2 plus c1 r2 the square. So that is beta is equal to j omega c1 r2 minus j omega. So write it as minus j omega into omega square r1 r2 square c1 square c2. J square is minus 1. So minus 1 into minus 1 is plus. It will be plus omega square r1 c1 square r2 minus j omega. J square is minus 1 into minus 1 is plus. It will be plus omega square r2 square c1 c2. Here also j square is minus 1 into minus 1 is plus omega square r2 square c1 square, that divided by 1 minus omega square r1 r2 c1 c2 the whole square plus omega square into r1 c1 plus r2 c2 plus c1 r2 the whole square. Fine students, hope all of you are following here. Okay, so the same equation is rewritten. Beta is equal to j omega, here j omega c1 r2 is taken common. J omega c1 r2, if we take it as common, right, then this is 1 into 1 minus, right, 1 minus omega square r1 r2 c1 c2. Okay, so here we are finding the that is common factor j omega c1 r2. So wherever there is j omega, here also there is j omega. So j omega c1 r2 is taken common. So if we take common here, it will be 1 minus of c1 r2. So 1 c1 r2 will go here. It will be omega square r1 r2 c1 c2. So it is 1 minus omega square r1 r2 c1 c2. Then plus omega square is taken common. Omega square, what else is taken common? Omega square c1 r2 is common throughout. So omega square c1 r2 is there here, c1 r2 is there here, c1 r2 is there here also. So if we take omega square c1 r2 here, so what will remain? C1 r1 will remain in the first term. So c1 r1 will remain, right? Plus omega square c1 r2, if we take common in the second term, omega square c1 r2, then what will remain? R2 c2 will remain. So R2 c2 will remain here, then plus omega square C1 omega square C1 R2. If we take common in the third term C1 R2, then what will remain? R1 R2 C1 will remain. So it is R2 C1 will remain. That divided by 1 minus omega square R1 R2 C1 C2 the whole square plus omega square into R1 C1 plus R2 C2 plus C1 R2 the whole square. The same denominator. Take it as equation number 4. Now, if we want to have a zero phase shift of the feedback network, then the imaginary part should be made equal to 0, or it must be 0. If the imaginary part is having the term, then we will not be having a zero phase shift. There will be some phase difference or phase angle present. So if we want to have a zero phase shift of the feedback network, the imaginary part must be 0. Fine. That is what is the imaginary part here, students. So it is j part is whatever is j part is, that is the imaginary term. So it is omega c1 r2 into 1 minus omega square r1 r2 c1 c2, right? That divided by, so plus omega square, this is the real term, second term is real term, omega square c1 r2 into c1 r1 plus r2 c2 plus c1 r2 is the real term. So this part is the imaginary j omega, whatever is j part, that is imaginary. So it is omega c1 r2 into 1 minus omega square r1 r2 c1 c2, that divided by 1 minus omega square r1 r2 c1 c2 the whole square plus omega square into r1 c1 plus r2 c2 plus r2 c1 square. This is equal to 0. The imaginary part must be made equal to 0 for zero phase shift of the feedback network. Then what will be here, students? The denominator into 0 will be 0. So it is omega c1 r2 into 1 minus omega square r1 r2 c1 c2, that is equal to 0. So this one, this into this is 0. So frequency cannot be 0. There will be some frequency omega. That means the 1 minus omega square r1 r2 c1 c2, that must be equal to 0. That is 1 minus omega square into 1 minus omega square r1 r2 c1 c2 is equal to 0. Or 1 is equal to omega square r1 r2 c1 c2, or omega square is equal to 1 divided by r1 r2 c1 c2, or omega is equal to 1 divided by square root of r1 r2 c1 c2. That is, what is omega, students? Omega is 2 pi f. That is 2 pi f is equal to 1 divided by square root of r1 r2 c1 c2, or f is equal to 1 divided by 2 pi square root of r1 r2 c1 c2. Take it as equation number 5. Usually R1 will be equal to R2, that is equal to R, and C1 is equal to C2, that is taken as equal to C. So if we substitute in the previous equation, that is equation number 5, R1 is equal to R2 is equal to R, and C1 is equal to C2 equal to C, then the equation will be F is equal to 1 divided by 2 pi into square root of R into C into C. That is 1 divided by 2 pi into square root of R square C square, or square root of R square C square is RC. Therefore, it will be F is equal to 1 upon 2 pi RC. Take it as equation number 6. Okay. So we have derived the equation for the frequency of oscillation of the Wien bridge oscillator here. Right. So starting with the figure here. So this is the figure of the oscillator, Wien bridge oscillator circuit. Starting from this figure and converting into an equivalent figure, then we have started the derivation of the frequency of oscillation of the Wien bridge oscillator. Right, first we wrote the equation for z1 z2, then replace j omega is equal to s, then we wrote the equation for I, it is v divided by z1 plus z2, or vf is equal to I into z2. So this vf is equal to I into z2, that is nothing but mean voltage v in into z2 divided by z1 plus z2. Then we wrote equation for beta, that is rearranging terms here, vf divided by vn is equal to, that is beta, that is z2 divided by z1 plus z2. Then we simplified the equation by substituting z1 and z2. Right, after simplification, then we replaced s by j omega, or s square is equal to j square omega square, that is equal to minus omega square. Then we rationalized the denominator. In the later step, we rationalized the denominator, right? And then finally we equated the imaginary part to 0 to have zero phase shift of the feedback network. So once we equated the imaginary part to 0, we got the equation for omega, that is 2 pi f is equal to 1 divided by square root of r1 r2 c1 c2, or f is equal to 1 divided by 2 pi to square root of r1 r2 c1 c2. Then we substituted r1 is equal to r2 is equal to r, and c1 equal to c2 equal to c, and later because of this substitution we got the equation as f is equal to 1 upon 2 pi rc. Right. Hope everybody have followed here, students. If there are any doubts in this derivation, please send your doubts to me. I'll clarify your doubts. Thank you.